solid state hydrogen storage materials, thermal energy storage, carbon dioxide capture, and absorption heating and cooling systems. He has published more than 100 papers in peer-reviewed international journals and proceedings of international and national conferences. Currently, he has executed 8 sponsored research projects worth more than 3 crores and some are in pipeline. He is editorial board member of Village Journal Energy Storage. He is a member of Project Review Committee for Technology Mission Division, Department of Science and Technology, India. He has reviewed more than 200 journal articles for eminent journals from elsewhere, Springer, VT Taylor and Francis, etc. He is serving as a member of Board of Studies and Board of Research for many autonomous engineering institutions. I welcome you, sir, and I request our resource person to take over the session.
Yes, thank you, madam. Thank you for your introduction. Can you see my presentation?
Yes, sir.
Yes, sir.
Yeah, now it is in presentation mode, right?
Yes, sir.
Yes, sir.
Yeah, thank you. Good evening, all. Thank you for inviting me to share my knowledge on hydrogen storage, especially. In this talk, I'm just going to cover about why hydrogen is considered as an energy carrier and what are the different challenges associated with implementing hydrogen as a buffer energy storage or an energy carrier, especially to integrate the renewables with the end users. So my talk majorly contains a brief introduction about the necessity of looking at alternative energy carriers or solutions when we want to use the renewables. Then I'll take up exclusively as hydrogen, why hydrogen, and how to produce hydrogen, and what are the different challenges in storing hydrogen, especially for transportation applications. And then utilization of hydrogen, especially for transportation. So when we integrate the hydrogen along with the other renewables for end users, how the energy spectrum looks like. So let me to start the talk with a brief introduction. I don't know what you have learned for the last 2 days, but anyway, the style or presentation may be slightly different about the necessity of looking about at the renewable energy sources. So we need energy for doing anything in our day-to-day life. We need energy for cooking, we need energy for transportation, we need energy for lightening, we need energy, whatnot. For everything, we require energy. Most probably we use it in different forms. For example, you take electrical energy, it has many applications. So now I am talking by sitting in Tirupati, IIT Tirupati, and you are listening at some remote place, all because of electrical energy that we are using to power our laptops, our desktops, our internet systems, everything. Okay, and similarly, we require energy for other day-to-day applications. So from where this energy is coming from? The energy is basically majorly coming from the primary source of energy is hydrocarbons. Okay, so we have coal mines, we have natural gas resources, we have petroleum resources. So these resources has taken a few million years to form. Okay, and we in school days itself we study that the process of formation of the coal mines or petroleum or natural gas mines, etc. So these take a few million years to form, but now we are exploring them and we are extracting them, utilizing them at a very rapid rate for the last 200 years. Especially after the industrialization. So we know that everything mechanization started with the first industrial revolution after the invention of the. So later petrol engine and diesel engine were invented, especially for transportation applications. then steam turbines, gas turbines followed. And all these, the energy conversion systems, basically we are converting the chemical energy into mechanical energy, and then from mechanical energy to electrical energy. All these systems are primarily dependent on the hydrocarbon based fuels, either coal, especially for electricity generation, and then petroleum based products for transportation, petrol, diesel in large, now to some extent natural gas. And for cooking, we are using mostly LPG. All these are primarily we are getting it from hydrocarbons. But we know that there is a ill effect of using these hydrocarbons at a rapid rate. So one major challenge is the depletion of these fossil fuel sources, because it takes a long period for the formation, but whereas we are using them at a very high rapid rate for 200 years, it is growing at the rate at which we are using them. So they are going to deplete in few decades or maybe centuries. Then the other problem of using these hydrocarbons at a rapid rate is we are burning these hydrocarbons by digging them from under the earth. We are taking out, then we are burning these hydrocarbons. When we burn hydrocarbon, what happens? It is nothing but a reaction of oxygen in the air with hydrogen and carbon in the hydro fuel. So it is producing carbon dioxide, carbon monoxide. So carbon dioxide is found to be one of the major reason for the global warming. So this is called as anthropogenic CO2 emissions, the man-made CO2 emissions. Of course, CO2 is emitted in other ways also, but this is man-made CO2 emissions. So the anthropogenic CO2 emissions are increasing exponentially for the last 150 to 200 years. Okay, so if you see the curve, which I'm not having here, so the rate is very rapid. Okay, so now we are maybe at between 350 to 400 ppm, parts per million. Okay, so once the anthropogenic emissions are increasing, so they are rising the global warming problem, because we know that we receive energy from the sun in the form of solar radiation. So the solar radiation is hitting the sun, the earth's surface. So while it is being hitting the earth's surface, some radiation is being absorbed, some is reflected, so we know the three phenomena. Some is transparent. So if there is no atmosphere surrounding the earth, we'll be having negative temperatures on the earth based on the properties, emissive properties, absorptive properties of the earth's surface. Since there is atmosphere, it is absorbing some radiation. So because of that, we have average positive temperatures on the earth. Okay. So this absorption, the gases absorbing radiation is called greenhouse effect, and that is increasing with the CO2 emissions. So all the countries came together through COP. Then they decided to reduce the CO2 emissions into the environment. So CO2 emissions are happening from all the sectors. If we compare the different sectors, this is a bit old figure, but still we can compare. Transportation is contributing to about 30% of the CO2 emissions. Okay, and we should able to mitigate the CO2 emissions. The other problem with the transportation is the vehicle population in cities, especially. Nowadays the city air quality is a big concern. If you look at the data related to Delhi, it is alarming. The air quality is very poor. Okay, because of the increase in number of vehicles within a city, especially in the local urbanized city area, because a lot of vehicles are moving and they release a lot of CO2. Okay, and so so it is a dynamic problem, unlike the other concentrated, or at a place if you are releasing the CO2, you can sequestrate it. There are methods to capture the CO2 that is being emitted by the industries or power generation plants. Most of the industries, at least so far, are located outside the cities. Now cities are expanding. The even industries are coming in the part of these cities. But nevertheless, at a fixed location, yeah, it is relatively easy. But the transportation is a major challenge in mitigating the CO2 emissions. So if you see, the vehicle population is increasing rapidly, especially in the Asian market, China and India especially. The rate at which the vehicles are coming onto the road is increasing, So far we are dependent mostly on petrol and diesel based vehicles. And most of this is imported with respect to Indian context. We are importing the petroleum, and through distillation we are making petrol and diesel. So it is going to cost a lot for us, especially the import cost is one of the major bill is from the import of the petroleum. So we have to look for the alternatives, how to reduce our energy dependency for transportation, and how to become self-resilient, and at the same time how we can reduce the CO2 emissions into environment without reduction in number of vehicles. Again, the number of vehicles are going to increase rapidly in the coming years. So some of the solutions, if you see, what are the possible solutions to reduce the fuel usage, conventional fuel usage, and thereby reducing the fuel cost, as well as reducing the amount of CO2 being emitted into the environment due to the transportation sector. So if you see, these are some of the possibilities listed here. One is increasing the efficiency of the conventional fuel systems. So this already a lot of work has been done in increasing the efficiency, thermal efficiency of the conventional engines for transportation applications, whether let it be auto cycles or a diesel cycle, or for air propulsion, it may be gas turbines. So everywhere, a significant progress has been done, and we know that the maximum efficiency of a heat engine is limited by the Carnot efficiency. So it says that 1 minus heat rejection temperature divided by source heat temperature. In the other way, the temperature at which we are rejecting it, the maximum temperature where we are adding the heat. So here, there are limitations. Okay, we cannot come closer to the Carnot efficiencies because of the lot of irreversibilities associated. We know that in Carnot engine, all the processes are reversible in nature. But whereas in actual systems, there are lot of irreversibilities because of the heat transfer and mass transfer and other fluid flow conditions. So one way of increasing the efficiency and coming closer to the Carnot cycles is we should be able to increase the temperature of operation, the maximum temperature of operation in these cycles. So that can be done only once we have the materials which can withstand a higher temperature for prolonged periods. And these materials should be machinable to the and it should also contain other mechanical and thermodynamic, thermophysical properties which are required for machining and manufacturing. Okay. So nevertheless, good progress has been done in increasing the temperature of operation. And the one challenge with using higher temperatures in case of IC engines is NOx formations. Okay. So that limits the maximum temperature utilization. But nevertheless, in steam turbines or gas turbines, this is going to be an advantage, because If you are generating electrical energy using steam turbines, the maximum temperature is limited to 600 degrees centigrade, since we are using water at a high pressure and high temperature. But nevertheless, the new material development has led to increasing the temperatures beyond 700 degrees centigrade using ultra high critical steam power plants. So thereby we are able to increase the efficiencies significantly. But nevertheless, still there is scope by understanding the processes, reducing the irreversibilities, by studying the entropy exergy analysis of different processes, and the manufacturing of the material methods. We should be able to come at least somewhat more closer to the Carnot efficiencies with respect to the conventional systems. Already a lot of work has been done in this regard, and the increase is very small. It's not a disruptive increase. Very incremental values only are being reported in the last decade or so. So to move away from petrol and diesel, the other option is compressed natural gas. Natural gas is relatively a cleaner fuel when compared to petrol and diesel, and easily combustible because it is in the gaseous state. But it is, as of now, is being limited to cities, metro cities. This is one possibility in future, by having a bigger network of pipelines through which we can circulate the natural gas. We'll be having pipelines of hundreds of kilometers in between with the pressurizing stations. So natural gas is pressurized for every 50 kilometers using the compression systems, and it is pumped back to the pipeline so that it can be circulated easily, using the piping network grid. But nevertheless, this is also a kind of a fossil fuel that will last for only for one or two, or may at the max 2.5 centuries with the existing resources or whatever is having now on the earth. The other option is to make it more sustainable. We can use agricultural products to make fuels. We call it as biofuels. So the major challenge is there are first generation biofuels and second generation biofuels. First generation biofuels, we are directly using the agricultural products, whereas in the second generation biofuels, we use the agricultural waste, especially like rice husk or corn cabs or bagasse, these kind of products. After extracting the food content from the agricultural products, we are using the leftovers for producing the second generation biofuels. So this is a promising way, and we are already, the government has already fixed some targets to mix the biofuels with the petrol and diesel, at least by 20 to 25%, so that we can reduce our fuel imports by 20 to 25%. That is a significant cost saving. But nevertheless, the challenge with the biofuels is the atomization and combustion characteristics of the fuels, because they are having high viscosity, so it poses some thermodynamic problems while being atomized like a diesel engine, or the diesel atomization we can study. So similar studies are being conducted to actually understand the spray characteristics or atomization characteristics of these fuels. There are many reports which seems to be promising. We can have a single fuel or a mixture of fuels which can be blended and used with petrol and diesel. The other option, which is seen to be disruptive, we are already seeing a transition of vehicles to electrical vehicles, two-wheelers, three-wheelers, and four-wheelers. Especially the transition is more fast in case of the two-wheelers and three-wheelers. Okay. So we can store the electrical energy in batteries, which can be used to drive the vehicle. So the major challenge associated with the electrical vehicles is the battery, the size of the battery, the weight of the battery, the time taken for charging the battery, the rate at which we can extract the electrical energy while vehicle being accelerated, and number of cycles it can be charged or discharged that is given by the life. So the major cost is and component is the battery in the electrical vehicles. There is significant improvement in the last 5 to 10 years in the charge carrying capacity of the batteries thanks to the lithium ion technology, and the how fast it can be charged. Now we have the very fast charging stations where the vehicle can be charged within an hour or 2 hours full charging. And there is, because the charge carrying capacity is increasing, the number of vehicles, the distance the vehicle can travel after full charging, one single charging is increasing. But nevertheless, if we look at the problems, the range is still limited. The cycles, number of charging and discharging has to be improved, and the rate at which the charging can be done also increased. Okay, so all these are all multidisciplinary problems, because if you are increasing the rate at which you can charge the vehicle, battery, then there is a lot of heat generation during this. Okay, so the battery management, especially thermal management of batteries, is going to be an important problem. Once you come up with the fast charging technologies, at the same time you should also develop safety technologies with better battery management or thermal management of the batteries. And other futuristic problem which is going to which is anticipated with respect to batteries is, once the life is over, how you will treat with the batteries. That will become again a challenge. It becomes a solid waste. Then we have to develop the recycling technologies. Of course, complete recycling is a challenge, especially with the lithium also. And then lithium is a limited resource, very few, that is also not sustainable in the long run. Then the other opportunity available is the hydrogen based fuel cell vehicles. Okay. And Indian government has already announced the National Hydrogen Energy Mission, Green Hydrogen Mission, where they want to generate hydrogen in an environmental friendly way and use it for different applications, transportation being projected as one of the applications. So the problem is, because we want to move from the hydrocarbon based fuels to renewable energy sources like solar or wind. India being a tropical country, we have a lot of solar energy available, and a lot of the cost is also long, so that we can install a lot of wind energies also. The challenge with the solar plants, solar PV plants or wind plants is this energy is highly intermittent in nature, and to use it for, let us say we are dependent on grid to transport energy from the power production state to the end users. And right now most of the grid is dependent on the hydrocarbon fuel based, coal based, to some extent hydraulic based power plants. So we know the capacity and how much we are going to produce, and we also know the demand pattern. There is a pattern for the demand, so we know supply and demand pattern, so we can easily manage the grid. But when it comes to renewables, especially solar and wind, these are highly intermittent in nature, and we know that solar energy is only available during daytime for a fixed time period, and that is also changes seasonally. During rainy season, due to cloudiness, we may not get any solar energy, or so it is not a fixed capacity energy harnessing method. Okay, so what we need to do when we are not sure of getting constant energy.
Excuse me, sir.
Yeah.
Sir, slides are moving, sir.
No,
I
no. The
think
slide is here only. Don't worry
same only,
about the
sir. Six,
slides.
six
Yeah,
only, sir.
yeah,
Okay, sir.
sixth
Thank you,
slide
sir.
only. I'm still giving introduction only. So why hydrogen is required, I'm just telling. Is it okay?
Okay, sir. Okay, sir. Thank you, sir. Thank you.
Yeah. I'm telling why hydrogen, apart from transportation, how it is going to play a role in integrating the especially intermittent renewable energies with the grid or end users. So when we don't have a surety about harnessing energy from solar or wind, then we have to install more higher capacities. So when we install higher capacity, if the demand is less, then we should be able to store the energy. No, storing energy is another problem. And when we want to store the few gigawatts of energy, the battery may not be a suitable solution, because we require large capacity batteries. Okay, maybe few multi-storied size batteries we require, which is not practically feasible. There are other methods, to integrate the renewables with grid level energy storage applications. One is using pumped water storage, where we need two reservoirs, one at a lower level, the other one at a higher level. So when you have the excess solar energy or excess wind energy, you can pump the water from a lower reservoir to a higher reservoir. And when you have insufficient solar energy or wind energy, the reversal of water takes place. The water passes from a higher elevation to the lower elevation through a turbine, generating the power. Okay, so this is a kind of solution, but it's not, may not be possible in all geometrical places. Some suitability is required, where you can construct two reservoirs with a elevation difference. Okay, so there are many other methods like compressed air storage and other technologies. So here hydrogen is envisioned as a kind of we can generate hydrogen using this excess solar or wind energies. So when we generate this hydrogen, means excess energy we are using to generate hydrogen, this hydrogen can be used for different applications, not only for transportation. The ammonia hydrogen can be used for producing ammonia, which is can be used for urea. Again, fertilizers is one of the important requirements with respect to Indian context. We import a lot of fertilizers. If we can make our own green ammonia and thereby urea, we can reduce the cost of imports of the urea, because being an agricultural country, we largely dependent on the imports of the urea. And not only that, we can use hydrogen in many industrial applications, like steel industry. So to manufacture steel, we want iron ore. Iron ore nowadays is treated using carbon monoxide, high temperature gases to reduce to iron. Then we can manufacture the steel. But if you can use hydrogen, then you can reduce the CO2 emissions from a steel industry. So there are plenty of industries, cement industry and many process industries, where you can use hydrogen directly as a fuel. So one of the method considered is you install more solar energy plants or more wind energy plants, higher capacity solar energy or a higher capacity wind energy plants than the required things. Then you use during the peak hours of, or when the excess energy is produced from these plants, you use it to generate hydrogen. And when you don't have sufficient solar or wind, then you use this hydrogen using fuel cells to generate the electrical energy, and which can be pumped to the grid. So it can be viewed as a kind of a energy balance method when you want to use for large scale energy storage. And not only that, we are generating fuel using this excess solar or wind energy, which can be used for many applications. Okay, transportation application or many heavy industries uses hydrogen directly. But what are the challenges, with respect to Indian context? What are the challenges that we have to work on or what are the technologies that we need to develop to realize hydrogen into the into the energy spectrum, where we can integrate the renewables with the end users, especially grid level applications or industrial applications, are using hydrogen as a fuel. So to before that, why we are considering hydrogen as a fuel is, if you see, as I told, any fuel is a mixture of carbon and hydrogen. Now the slide has changed, right? We are at slide number 7. Pardon me?
Yes, sir. Yes, sir.
Yeah. You can see the slide, why hydrogen.
Yes, sir.
Yeah, okay. Yeah, any fuel is a mixture of carbon and hydrogen, and the amount of energy released when we burn 1 kg of fuel or any quantity, for example 1 kg of fuel, depends upon the calorific value or the heating value of this fuel. So basically it is a oxidation reaction. CH reacts with O2 and forms CO2 and H2O in a stoichiometric air fuel mixture. Or if it is a lean mixture, means less air is available, then more fuel and less air is available, then CO is formed, because of the incomplete combustion of the carbon. So carbon, so when we see the reactant and products, the CO2 formation gives relatively less energy when compared to H2O formation. Yes. We can calculate the formation enthalpies based on the individual, the formation enthalpies of the reactants and products. So in a fuel, when we move from heavier carbons to lighter carbon, what do you mean by heavier carbon and lighter carbon is? Heavier carbon means in the molecule of the fuel, you will have more carbon atoms. That means then it is a heavier carbon. When you have more hydrogen atoms in the molecule when compared to the carbon atoms, it becomes lighter. For example, if you take coal, it is mostly carbon, so it is in the solid state. When you have more hydrogen atoms in the molecule, it becomes oil, petrol, diesel kind of thing. And you have still more amount of hydrogen atoms, CH4, it becomes a gas. And when you don't have carbon atoms, it is pure hydrogen. So the heating value increases once you move from more heavy carbons to lighter carbons or more hydrogen atoms in the molecule. So since hydrogen is only pure hydrogen you have, there is no carbon atom. The energy density is quite high. Okay, that means per unit mass, it has large energy. That means once you burn 1 kg of hydrogen, you will get more amount of energy. And moreover, hydrogen is abundant, may not be as a single element, but in combination with carbon and oxygen, all organic compounds are in hydrogen contains along with the carbon. And in case of water, it is mixed with oxygen. Okay. So it is abundant element. Even in sun, we have a lot of hydrogen which is getting transformed into helium continuously. So when you compare the properties as a fuel, it is almost having thrice the energy per kg when compared to that of the petrol. It has a high self-ignition temperature. The flame temperature is comparable with the gasoline. It has very high ignition limits. So this is a kind of both advantage and disadvantage, because even you have very lean mixture, very small amount of fuel and hydrogen, large amount of air also, it becomes ignitable. Okay. The major challenge is the once hydrogen is being leaked, because it is the lightest element, it can diffuse very easily, and diffusion coefficient is very high, when compared to methane and gasoline. And we don't have any reagents which can diffuse at the same rate of hydrogen. So hydrogen is odorless and colorless. Even the flame is colorless. So it is difficult to follow the hydrogen flame. Okay. So we can't mix any reagents, and so it is safety wise, we have to take more steps, because we need to use sensors to detect the hydrogen leakage, etc. Okay. So as a fuel, it is good. when compared to with the methane and the gasoline. So what are the challenges are to realize hydrogen as a vertical in the energy spectrum, overall energy spectrum is producing hydrogen in a environmentally friendly way, in a efficient way, cost effective way. We should be able to produce hydrogen. Of course, hydrogen can be produced from electrolysis using the renewable energies or even normal electricity. We can use fossil fuels with reforming process. We can produce hydrogen. Bio or bio-inspired processes. A lot of work is going in this area also. Or we can use cracking of water, thermal cracking of water. We'll see briefly about the hydrogen production. But the major challenge is how you store hydrogen and transport it. That is going to be a major challenge. Once you have larger capacity solar plants or wind plants, you can generate a lot of green hydrogen. But once you generate it, how you can transport it to the end user. Okay, how you can store and transport it to the end user, and at the end use, how efficiently you are using it. Okay, so you can use fuel cells to directly convert the hydrogen energy, chemical energy present in the hydrogen, into electrical energy or even the thermal energy. Or you can use combust hydrogen in IC engines, especially for transportation applications. And the electricity generation, you can use, I also use using fuel cells, especially in the high temperature fuel cells like solid oxide fuel cells to produce the power. So if you see with respect to hydrogen production, these are the current technologies available for hydrogen production. At present, most of the hydrogen is produced by steam reforming, especially natural gas as the feed. Nearly half of the hydrogen produced as on date is from this process. This is scalable. You can produce large quantities of hydrogen, using this method. And this is the cheapest also at present. Steam reforming is one of the cheapest method of producing hydrogen. Then partial oxidation of heavy hydrocarbons. This is a kind of a similar method. Need not be natural gas. You can use higher hydrocarbons, means heavier hydrocarbons compared to methane, because methane has 4 hydrogen atoms. If you have lesser hydrogen atoms, then you can partially oxidize and get hydrogen. Or partial oxidation of coal. This is also, coal means only mostly it is carbon and there is some hydrogen in it. You can produce hydrogen by separating hydrogen from the organic molecules. But all these processes, we are using fossil fuels where it contains carbon. We are separating hydrogen from the carbon, and we are generating carbon dioxide during the process. So this is called gray hydrogen. The hydrogen produced with emission of carbon dioxide is called gray hydrogen. Of course, there is a lot of colors given nowadays for hydrogen produced, depending upon the feedstock, what feedstock you are using to produce hydrogen, whether it is coal or whether it is heavier hydrocarbons or lighter hydrocarbons like natural gas. So whatever way it is, if it is produced with the reforming process with a lot of CO2 emissions, it is called gray hydrogen. And if you can capture the CO2 during the process, means you are not letting the CO2 go into the environment, you are capturing the CO2 during the process and sequestrating it, then it is called blue. Yeah. So where we have to avoid the CO2 emissions by carbon capture and storage and sequestration, then this is fine, because it is most cost effective right now, because cost matters a lot. At the end of the day, whatever the fuel we want to use for transportation, it should be comparable with the petrol and diesel. Otherwise, if it is very costly, no one wants to use it. Okay. In that way, electrical energy seems to be promising right now, because the operation cost is less, even though the initial cost is higher, the battery cost is higher. But again, how frequently you have to change the battery, that matters in the overall cost of the vehicle. So then we want to move away from this carbon emissions during hydrogen production and make the process more cleaner, or to avoid the CO2 or CO emissions into the environment. Then we have to use the electrolysis process. But electrolysis is a costly process, because we need electrical energy to split the hydrogen, water into hydrogen and oxygen. But it gives pure hydrogen, unlike the, if you see all these reactions, whatever the final reaction you are having is, you have CO2 and H2 in this reaction, or CO2 and H2 in this reaction. We have to separate hydrogen. Whatever the method we are using to separate or purify hydrogen, some traces of this will be still there. CO2 or CO will be there. Okay, so we'll get not very high pure hydrogen, maybe of the order of 99.99 order, but using electrolysis we can get 99.49 order of the order pure hydrogen, which is basically required for, especially for fuel cell applications. Once you take IC applications, you can have some impurities, no problem, without much problem. But in case of fuel cell applications, you want very high pure hydrogen to convert that into energy, because the electrodes are again sensitive to these impurities in hydrogen gas. Okay, so the immediate challenge is, we should be able to move from these present technologies, which are basically based on the reforming process, natural gas, petroleum, or coal reforming processes or gasification processes. We should move towards cleaner and more sustainable methods for hydrogen production. So as discussed, you can use solar and wind for through electrolysis to produce hydrogen. The major challenge is here is to reduce the cost of hydrogen produced through these methods. Okay, at present it is at least 3 times costlier than the hydrogen produced by reforming process. So we should be able to develop electrolyzers of high capacity electrolyzers at a lesser cost, and the electricity should also come at a lesser cost, so that we should be able to make hydrogen produced in a greener manner, or cleaner manner, more sustainable. Okay, so we should be able to reduce the cost. We should be able to scale up the hydrogen production rate. And biomass, a lot of work is being done, and but again, the scaling up issues are there right now with biomass, but future they may solve that also, where we can use through gasification or pyrolysis methods to produce hydrogen. And nuclear is a question mark still, because many of the European countries, as we know, moving away from the nuclear because of the nuclear waste. Otherwise, you can use nuclear energy also, because there is no CO2 emissions. But at the end of the day, we have to deal with the nuclear waste. So there are many opportunities available, and with respect to hydrogen production, especially with respect to electrolysis, developing a large size electrolyzers. Now, indigenously, we don't have this technology, because our capacity is limited with respect to electrolyzers. SECRI or BARC or some of the industries, as well as academic institutions, has developed the electrolyzers, but of the very few kilowatt capacity only. But to generate at a larger scale, we need gigawatt capacities. But industries, bigger industries, has hired this technology, and they're installing capacities of few gigawatts. So once you have this green hydrogen in hand, then how do you transport it? Why hydrogen transport or storage is a problem. So I will come back to this slide again. Let us see what is the problem associated with the hydrogen storage. This is the figure which shows the gravimetric energy density as well as volumetric energy density. So what is the difference between gravimetric energy density and volumetric energy density? So gravimetric energy density shows that per kg of the fuel, how much energy it contains. Okay. So in this diagram, if you see, the hydrogen has a larger gravimetric energy capacity. You can see there is nothing in this range. But when it comes to volumetric density, that means per liter at normal temperature and pressure, what is the energy content of the hydrogen? It is very poor. You can see, very less than 10 in, whether it is in compressed state or very high pressure compression storage state or liquid state is much lower when compared to the other fuels. Okay, the volumetric density is very high. So why volumetric density plays a vital role? Because it all depends upon the volume in which you can store the fuel for transportation application. If you take a typical two-wheeler, you can see the tank size of your petrol tank, right? Or a four-wheeler also, you can realize the tank size. So once if the volumetric density is less, that means you want a huge volume to store the hydrogen. That is not practical especially for the transportation applications. So we should be able to increase the volumetric density of hydrogen storage. So US government Department of Energy, this is taken from their site, has given some specifications to use hydrogen as a fuel for the transportation applications. One is the system gravimetric capacity is the first parameter. So these are being revised, because it's not so easy to achieve these targets. So they are being revised 2-3 times in the recent years also. So ultimately, you should have a gravimetric storage capacity of 2.2. That means weight percentage. If you take the overall size of the system, that means overall the storage device is, let us say, some 100 kgs. So you should be able to store at least 2 to 2.5 kgs of hydrogen in that. Similarly, the volumetric capacity per liter, you should be able to store at least 1.7 kgs of hydrogen. The cost is also important, because at the end of the day, even though you have hydrogen, you can reduce the production cost of the hydrogen. If you won't handle it, the storage and transportation at a lesser cost, at the end user has to pay more for the hydrogen. So the cost should be less, especially at least it should be less than $8, per kg of hydrogen. So the overall the fuel cost is dependent on all these parameters. Then, as we have seen, it has a very high gravimetric energy density. How we can increase the volumetric energy density of the hydrogen? So here it is shown hydrogen at 700 bar and 350 bar, but at normal temperature and pressure, at room conditions, let us say 1 atmospheric pressure, almost 1 bar, and a normal temperature maybe around 27 degrees centigrade, 300 degrees, 30 degrees centigrade. The volume, specific volume of the hydrogen is very high, or the density is very less, 0.0189 kg per meter cube. That means, if you take 1 meter cube volume, you can visualize 1 meter cube volume, right? 1 meter cube volume, and then if you are storing hydrogen in that 1 meter cube volume at room conditions, okay, atmospheric pressure and room temperature, then you can store only 18.9 grams of hydrogen. It is very less. The 1 meter cube size, it is very less. So we should be able to increase the volumetric energy density. That can be done by putting more amount of hydrogen in the same volume. How we can put more amount of hydrogen in the same volume? One is we can pressurize, and put hydrogen in that. Okay, so if you take the conventional hydrogen supply tanks, you can see the red color tanks, which can store up to 150 bar. That is conventional metallic cylinders. You can store only up to 150 bar, but that is not sufficient for to meet the vehicular applications. So you have to increase up to 700 bar. So these metallic cylinders cannot withstand pressures, such a high pressures. Okay, so you need to develop type 4 cylinders. This is metallic cylinders are type 1. Then there are type 2, type 3, and type 4 cylinders. Type 4 cylinders, you have a composite liner and a composite structure to store the hydrogen. So where you can go up to 700 bar. So the first method is compressing hydrogen, okay, to a very high pressure, of the order of 700 to 800 bar and storing it in type 4 cylinders, which are made of composite materials. But these are not so easy because developing these composite cylinders and fabricating them and testing them is a challenge. At least now in India, we don't have any testing facility to test the hydrogen cylinders. If you want to store it at 800 bar, you need to test it at least up to 1500 to 1800 bar. Okay, then only you will allow to use it at 800 bar. So testing is a major challenge. The developing of these cylinders is one challenge. The other challenge is how you can compress the hydrogen from let us say electrolyzer pressure, outlet pressure to such a high pressure. Let us say the electrolyzer outlet pressure is nowadays we are getting the the higher pressure outputs even up to some 30 bar, 30 to 40 bar from the electrolyzers, but we need to still compress it to 800 bar. So maybe during the next lecture I will be talking about, not today, on I think on 19th, today 20th, I think I'll be talking about the application of metal hydrates for compressing the hydrogen using the thermal energy. Because otherwise, if you use mechanical compressors to compress hydrogen to such high pressures, will be requiring a lot of electrical energy. Okay, we know that the exergy associated with this electrical energy is quite high. So we can use, if we can use the low exergy energy like thermal energy at a lower temperature, then the energy required, the quality of the energy required for hydrogen compression can be reduced. And that is a challenge. People are working, developing different types of compressors apart from mechanical compressors, because all mechanical compressors have moving parts, and moving part means you need lubrication. Once you have the lubrication, the lubricant can mix with hydrogen, it will pollute the hydrogen. So non-moving, non-mechanically moved compressors being developed for compressing the hydrogen. So the other option of storing the hydrogen or increasing the volumetric energy density of the hydrogen is to liquefy it. Once you change from any fluid from vapor state to liquid state, we know that its density increases or specific volume reduces. So thereby you can store more amount of hydrogen in a given volume. But liquefaction at 1 atmospheric pressure needs to lower the temperature to 20 Kelvin. That is about minus 253 degrees centigrade, very low temperature. So we need cryogenics. This is also highly energy intensive process. We require multiple combination of multiple processes. At least we need a cascaded vapor compression refrigeration systems, or multi gas gasification systems like cryocoolers, or the Joule-Thomson expansion method we can use. But every method you need to compress the gas to very high pressures before being liquefied. It requires a lot of energy to liquefy the hydrogen. So even you liquefy it, it means you bring the temperature to 20 Kelvin and you store it at 20 Kelvin. The surroundings being at room temperature, you need to insulate it. Even you insulate it, there is large temperature difference. For example, the environment temperature is, let us say, 300 Kelvin, okay, 27 degrees centigrade. Then there is a temperature difference of around 280 Kelvin or degrees centigrade between the atmosphere and the liquid hydrogen. So there will be heat leakage into the hydrogen storage tank, and once it is being heated, it gets converted into vapor. As the vapor is being accumulated in the liquid hydrogen tank, then the pressure increases. So to keep the pressure within the safety limit, we have to let some hydrogen go off from the cylinder. So that we can do it using the safety valves. Once the pressure increases beyond certain pressure, the safety valve opens and the hydrogen comes out. So that is called boil-off losses. But nevertheless, liquid hydrogen is still used for space applications, especially for using along with the electronic fuel cells to give the energy to the electronic components in the satellites. And Airbus also has announced the aircrafts being operated in future using hydrogen as a fuel, especially stored in the liquid state. You know that Airbus is one of the leading aircraft manufacturers along with the Boeing. So they have plans to develop liquid hydrogen tanks which can be used for propulsion of the aircraft. So the other option is you can further increase the volumetric density, or you can reduce hydrogen into a solid state. Then how you can convert hydrogen in solid state? If you purely convert hydrogen into solid state as a single element, you have to reduce the temperatures to very low, near to 0 Kelvin states. The solid state, not 0 Kelvin, but nearer to that. So that is very difficult. So what you can do is there are materials which can absorb or absorb material. Absorption is a chemisorption process where the hydrogen goes into the interstitial space of a molecule. It occupies the entire volume of the particle. So whereas adsorption is a physisorption process where the hydrogen sticks over the molecule surface. Okay. So both absorption or adsorption are extensively studied to store hydrogen in the solid state. So let us see briefly about what are the chemisorption materials. Chemisorption materials are metal hydrates. Examples are metal hydrates and complex metal hydrates. So metal hydrates are a kind of intermetallics or alloys which can readily absorb or desorb hydrogen near atmospheric conditions. They are proven to be reversible. They are stable for a few thousands of cycles, where the hydrogen can be reversibly absorbed and desorbed cyclically and continuously. In case of complex metal hydrates, but there the problem is the most of the metal hydrates are heavier metals, so the hydrogen storage capacity per mass is limited. Okay, the gravimetric storage capacity of the material is limited near atmospheric conditions to less than 2 weight percentage, maybe at higher temperatures like 300 and 350 degrees centigrade, it can go up to 6 to 7 weight percentage. That means 100 kgs of the material can store 6 kgs of hydrogen. Okay, only material alone. If you consider the entire system, it further reduces, may become 1/4, because we have seen the US DOE requirement of overall system should have a gravimetric hydrogen storage capacity of more than 2. Okay, so that is seems to be difficult at present stage, especially with the metal hydrates. But metal hydrates are very good materials because they can absorb, desorb hydrogen reversibly near atmospheric conditions. So there are many applications of metal hydrates apart from hydrogen storage for transportation applications, which we are going to see in the next lecture on 20th. And the complex metal hydrates, yes, they are lighter when compared to metal hydrates, but that means they can, per mass, they can take up, per unit mass, they can take up more amount of hydrogen, they can store more amount of hydrogen, but they are not reversible right now, because once you heat them, they will release hydrogen, but inside too, then and there hydrogenating these materials is difficult. Okay. So the other option is the hydrogen sticks on the surface of the solid adsorbents. That is like mostly these are all carbon based materials. We'll see briefly about activated carbons and carbon in different forms, like single wall carbon nanotubes, multi wall carbon nanotubes, fullerenes, graphene, graphite. All these materials are well studied to understand the absorption behavior of hydrogen at cryogenic temperatures as well as at near ambient conditions. And metal organic frameworks are also extensively studied. Seems to be a kind of a promising material with a high hydrogen storage capacity when compared to the activated carbons. So if you see the reversible as of now are the metal hydrates. Based on the kind of material we use, these can be classified majorly as AB type, AB2 type, AB5 type, and A2B type. Okay. AB type are titanium based, like TAFE being the best example. So TAFE, titanium, if you expose hydrogen, it won't absorb hydrogen near atmospheric conditions. You have to use very high pressures or very high temperatures. Okay, but the requirement for transportation applications is we should be able to store hydrogen near ambient conditions. Okay, so then you can alter the thermodynamic properties by mixing other elements with titanium. For example, TAFE, which can readily absorb hydrogen near atmospheric conditions, but it has a weight capacity less than 2 weight percentage. The one challenge with TAFE is the activation is very difficult. For activating, for make it to absorb hydrogen, we have to heat it to high temperatures. But once it gets activated, it can readily absorb and dissolve hydrogen at near ambient conditions. But many other substitutions are possible, like titanium can be substituted with other elements, or Fe can also be substituted with other elements. There are hundreds of compounds studied in AB type to alter the thermodynamic properties. That means the property, pressure and temperature where the hydrogen is being absorbed and dissolved, the equilibrium conditions. And they are partially successful to reduce the activation requirements. The other type is AB2, that are ZrV2, ZrMN2, these kind of materials. They are also found to be very good for hydrogen absorption and desorption. And the third type is rare earth based, like LaNi5 or MMNi5. They are excellent materials for hydrogen absorption near ambient conditions. And the properties can also be easily tuned, either by substituting for lanthanum or nickel. If you take LaNi5, lanthanum is a rare earth based element. You can substitute other cerium, praseodymium, like kind of, some transition elements or other elements like aluminum, cobalt, nickel, ferrous for nickel, and obtain a variety of thermodynamic properties. So we can obtain a variety of thermodynamic properties. The challenge with the first three type of metal hydrides, especially AB type titanium based hydrides, or AB2 type zirconium based hydrides, or AB5 type rare earth based hydrides, the challenge is their weight percentage is limited. The gravimetric capacity is less than 2 weight percentage. Okay. So, but magnesium can give a higher gravimetric hydrogen storage capacity, but it should be operated at higher temperatures of the order of 300 to 350 degrees centigrade. So at 300, in the range of 300 to 350 degrees centigrade, magnesium can absorb up to 7 weight percentage, 6.5 to 7 weight percentage easily. So that's a good amount, but the operating conditions has to be lowered, especially for transportation applications. And believe me that thousands of papers being published on magnesium based hydrides to study how to reduce the hydrogen absorption desorption characteristics, bring down nearer to the atmospheric conditions. So the magnesium based hydrides, many intermetallics are formed, like Mg2Ni or MgAl based intermetallics, and many oxides being as added as catalyst, or many composites being formed. To some extent, it is they are partially successful because they can bring down the weight percentage, the hydrogen storage absorption desorption temperatures nearer to 150 degrees centigrade, but the weight percentage are not achieved up to 6 weight percentage near 150 degrees or 200 degrees centigrade. It is coming down to 2 to 3 weight percentage. Okay. So the metal hydrides are excellent materials for hydrogen storage, but the major problem associated with metal hydrides is their gravimetric hydrogen storage capacity is limited. Okay, if we can find out a combination of materials, because now everyone using AIML techniques to study to take the base elements and a combination of to combine them in different compositions, and to study the possibility of achieving the higher hydrogen storage capacity, or higher favorable thermodynamic properties. So that study is still going on. So once you take the metal hydrates, the containers of metal hydrates looks like this. These are called hydrate stores. If you take see the cylinders can be arranged. Each cylinder contains a lot of metal hydrate in this. This is like a shell and tube kind of heat exchanger where the entire cylinder is filled with the metal hydrate, and you want to insert tubes of hydrogen supply lines or hydrogen extraction lines through this, through which hydrogen can be go into the metal hydrates or come out of the metal hydrates. And here the absorption and desorption are exothermic and endothermic reactions. So you should be able to supply the heating or cooling fluid, heat transfer fluid through this tube bed. So basically any metal hydrate reactor contains the material which is the metal hydrate, an alloy or intermetallic, and then the elements, especially the heat transfer tubes and hydrogen supply or extraction filter kind of tubes. Okay, so this we can develop containers like this, by arranging many cylinders which contains metal hydrates in different forms, and we can carry along with the vehicle. So if you compare the three methods, like storing hydrogen in compressed gas form, or storing hydrogen in liquid state, or storing hydrogen in solid state, especially using metal hydrate, the comparison goes like this. Again, this is a kind of a old paper published in Nature. Nature is one of the very leading scientific journal, okay, well recognized and well appreciated journal, with very high impact factor, of course. So if you want to use hydrogen as a fuel to run a vehicle for a particular distance, other factors being same, we can see the volume occupied by the gas in different storage technologies. For example, you compress the gas up to 200 bar, then the container size is of this much volume, and if you liquefy it, the volume reduces. Then you use a metal hydride which is near ambient conditions like LiNFi. As I told, the weight percentage is limited to 2 weight percentage near ambient conditions. So with the lesser gravimetric capacity, the volume is this much. If you can increase the volumetric capacity further, the gravimetric capacity of the solid material further, the volume further reduces. Okay. So this is a nice comparison of the volume, because as I told, the volume is very important. How much volume we require for transporting a certain amount of hydrogen is very critical. We should be able to reduce the volume. At the same time, the storage device mass is also very, very important. So the other methods other than metal hydrates is the complex metal hydrate. Some of the examples are alanates and borohydrates. So sodium aluminum hydrates, or boron or lithium aluminum hydrates or borohydrates. Of these hydrates, they are very good for hydrogen storage, because all these materials, if you take sodium aluminum hydride or lithium aluminum hydride, even magnesium aluminum hydride, all these contains a lot of hydrogen, because these are lighter. If you take lithium, it is much lighter. But the challenge is the hydrogen dissociation from these materials is a multi-step process. Okay, so once you are heating sodium aluminum hydride, it releases hydrogen, in a two-step process. So if you see here, at a higher temperatures, it releases some hydrogen, and then at a somewhat lower temperature, again it releases again. Okay, so it is a multi-step process. They have very high hydrogen storage capacity. If you see in this slide, the lithium aluminum hydride has a very high hydrogen storage capacity of the 10.5 weight percentage, and it's quite high. But the challenge is the hydrogen release is easier if you heat it to maybe up to 300 or 350 degrees centigrade, but you cannot make it reversible in situ. Okay, you cannot make a lithium aluminum hydride back by sending hydrogen back to the lithium LiAl. So that is difficult. So reversibility is not achieved so far with the complex metal hydrides. A lot of work has been done. Thousands of papers are produced in this area also, but commercially and at practical level, this is not achieved so far. Still, people are studying these hydrides, complex hydrides. So the other option is, as I told, the adsorption materials, activated carbon. It can be right from coconut shell or many other feedstock can be used for producing the activated carbon. Just a second, let me to take a sip of water. So generally these activated carbons are high porous material. It has larger surface area, and they can absorb the hydrogen. It is found that these materials are good at cryogenic temperatures, let us say of the order of 77 Kelvin, but at atmospheric conditions they require high pressure again to store hydrogen. A lot of studies have been done with all the materials with different doping technologies, with nickel doping, platinum doping, palladium doping. Okay, but again here if you see the pressures required are quite high. So they may not be suitable right now, especially for the kind of transportation application, because again once you make it compact, they lose the surface area and the porosity reduces, especially when you want to put it in reactors and use like metal hydride kind of structures. The other one is carbon nanotubes. These materials have so many applications apart from hydrogen storage. They are wonderful materials with larger porosity and higher surface area with high thermal conductivity. They are used for the different electronics applications also. So they are also studied for hydrogen storage. Again, the results found to be similar. They are good at cryogenic temperatures, but at room conditions, the demonstration of reversible hydrogen storage capacities of the required weight percentage is limited. So now that's why there is no major breakthrough through even with the carbon materials for the hydrogen storage. The other important aspect is once you have these metal hydrides, especially for either transportation or applications, even you achieve a higher weight percentage, how you design these reactors, this is are the hydrogen storage devices which are solid state based. Okay, so this is a kind of a major challenge because the hydrogen absorption in these materials is exothermic and desorption is endothermic. Since the hydrogen absorption is exothermic, as the hydrogen being absorbed, a lot of energy, heat energy is released. If we won't remove this heat energy from the metal hydride bed at the rate at which it is being released, then what happens is the energy gets accumulated within the bed so that the temperature of the bed increases. So when the temperature of the bed increases, for like any absorption process which is exothermic in nature, the rate of absorption reduces with increase in temperature. Similarly, while the hydrogen being dissolved, we should able to supply heat energy at the same rate at which it is getting down, because it is consuming energy so that the temperature of the bed keeps dropping while the hydrogen is being dissolved. That is a kind of endothermic reaction. So we have to supply this heat energy very effectively. So it is kind of a overall heat and mass transfer problem where we should able to maintain good heat transfer, thereby good mass transfer for hydrogen absorption and desorption. So these reactors can be either liquid cooled or they can be gas cooled. If it is gas cooled, the heat transfer coefficient, we know that the convective heat transfer coefficient is very less. So we should be able to increase the convective heat transfer coefficient by inserting the fins, okay? Especially for the gas side, not solid side, on the gas side. Of course, solid side also it is required in case of metal hydride beds, because the thermal conductivity of the metal hydride beds is very less. So we need to study systematically these devices, the solid state hydrogen storage devices. So the first configuration shows a shell and tube kind of heat exchanger, where the shell side, the entire shell is filled with metal hydride. You can see here the larger circle in this very smaller circle, which is hollow circle, is the heat exchanger tube through which the hot fluid or cold fluid is sent. Hot fluid is sent for the hydrogen desorption, and the cold fluid is sent for the keeping the bed at a lower temperature during hydrogen absorption. And the filled smaller circles are the hydrogen supply lines. These are the filters. Okay, so if you take a bigger tank where we fill metal hydride and we have a large number of coolant tubes, and we want insert a large number of hydrogen filters, then we have to optimize the overall the size and the weight of the storage device. So the other two figures shows the gas cooled arrangement, where we use different kinds of fin arrangements. Here it is used plate fins, and the other one is the radial fins. Okay, so once you have the devices, we have to design them carefully for their geometries, tube length, the diameter of the tubes, the number of the arrangement of the heat transfer fluid tubes, and the filter tubes, everything. So for that, a heat and mass transfer analysis is required. So we can take a base element, and we need to which can represent the actual system by uh, you know by just extending it in all the three directions. Then we need to define the conservative equation, especially mass conservation, and then energy conservation, then diffusion equations. So all these equations need to be applied to this finite the unit cell we have taken. Then we have to solve it using a solver, or we need to develop a code. In this case, one of my colleague worked at IIT Madras. He used the COMSOL multiphysics to solve the simultaneous partial differential equations of the mass diffusion and energy equations. So if you see, the initially the bed is like this. So as uh, the hydrogen being absorbed, the material gets converted from blue color to red color with the time. We can see at different locations of the bed how this temperature as well as concentration is varying. For example, I can run a video and show it to you. um, the the hydrogen absorption process. Can you see the video?
Sir.
Yeah,
Playing,
you
sir.
can.
Playing, sir.
Yeah, you
Playing,
can
sir.
see. Suppose again, I'll come back from the beginning. In the beginning, it is in blue color. You can see the region next to the coolant tubes are turning faster into red. Okay, so we can see that where the heat transfer is good, we obtain a better heat transfer. There, the bed is getting saturated with hydrogen faster. Okay, and that is slowly diffusing into the other region, which is far away from the heat transfer tube. Okay, I will get back to my presentation. So like this, we can do similar studies with the other tubes also. But the aim of this study is know how you can achieve a better mass transfer by optimizing the heat transfer, and you need to reduce the overall weight as well as the size of the size means the volume of the tank. So both mass and volume of the tank you should be able to reduce. So for example, if you see whatever design he has considered, it is requiring almost the system it is coming to 370 kgs for storing 2 kgs of hydrogen. So the overall hydrogen storage capacity is much less than 0.5 percent, whereas we require 2 weight percentage. Okay, so right now that is why The metal hydrides are not commercially considered for transportation applications. Only the type 4 cylinders are being used for the transportation applications. You might have studied or seen YouTube videos that almost all countries are riding hydrogen based trains. Even in India, the government is planning to launch a hydrogen based train soon. Okay. So these vehicles are normally run by the fuel cells. So why we use fuel cells is fuel cells are having a higher efficiency. Here, this slides compares the efficiency of the fuel cells with other engines. Conventional engines like gasoline engine, then a diesel engine, or steam turbines or gas turbines. They're much ahead of the efficiency wise. The fuel cells, because you are the conversion is direct. No intermittent conversion. You are directly converting the chemical energy into the uh, electrical energy. Of course, fuel cells is not new. Way back, the research on fuel cells started in 1800s. You can see in these slides, the General Electrical invents the proton exchange membrane fuel cell around 1950s. Then NASA used its first fuel cell for space missions in 1960s. Okay, so they're well developed technologies. Of course, not within India. At least abroad, they are well developed technologies. So this slide shows the working principle of a proton exchange membrane fuel cell. Um, okay, so it shows that there is two electrodes and a membrane. Then, as the name suggests, it allows only the proton through it. We know that hydrogen has one proton and one electron. It doesn't have neutron. So at the one of the electrode, the catalyst divides. It splits hydrogen into electron and proton. Then this membrane allows only proton to pass through this. Then the electron has to pass through the external circuit. Okay, so we know that passage of electrons is nothing but generation of electrical energy. We can see that this bulb is glowing when the electrons are passing, and again here the proton and electron mixes with oxygen forming water. So the output from the waste product from the fuel cell is water, H2. Okay. So based on the temperature of operation, the fuel cells are categorized like this. The first one is a proton exchange membrane fuel cell, operates near ambient conditions. Then the phosphoric acid fuel cells, then alkaline fuel cells, that is AFC. Then the highest temperature operated is solid oxide fuel cells. A lot of work is being done because they are suitable for power generation applications. You can also produce steam from that, at 900 and 1000 degrees centigrade, because they are being operated at such a higher temperature. Not only electrical energy produced from the fuel cells, but also from the steam turbines can be run because at a higher temperatures. The major challenge is each cell gives a very limited voltage power output. So you have to arrange a lot of cells. You have to stack a lot of cells as if we are doing a battery pack where we take cell kind of thing, cell kind of batteries, a number of batteries, we pack them, and we want to manage the power output from it. We want to manage the thermal thermal management of it. It should not get fired because of the high temperature produced during charging or discharging of the battery. Same problem exists with the fuel cells also, because a single cell gives a limited power output. To get a reasonable power output, we have to stack a number of cells. When we are stacking a number of cells together, then hydrogen flow pattern, then thermal management of this packing, these problems come into existence. Of course, it is a well-studied problem, and not within India. Again, in India, we have a limited capacity stacking only as of now. But worldwide, if you see, you can get even from 1 watt capacity to 1 megawatt capacity stacks, where you can produce power of such a lower capacity to very high capacity. So nevertheless, the overall conclusion from this talk is we should able to produce hydrogen in a environmental friendly way, sustainable way, because again, if you dependent on hydrocarbon fuels, it is not sustainable because those fossil fuels are going to exhaust sooner or later. Then the option is you should able to use water, either it is clean water or salty water also you can use it, is the question mark. Then use these renewable energies in a greener way to produce hydrogen. Then develop technologies to transport hydrogen, like natural gas. We are not able to transport hydrogen at right now with through the pipelines, because many metals reacts with hydrogen and they get damaged. That is called hydrogen embrittlement, which is not yet understand completely. So right now the proposal is to mix 20% of hydrogen with natural gas and circulate and use it as a fuel. But nevertheless, the technology need to be developed to circulate 100% hydrogen. Otherwise, we can store hydrogen in the form of compressed gases storage, or liquid storage at very low temperatures, or we need to develop still solid materials which can store hydrogens with a larger weight percentage. Okay, so once we realize this, we can move from completely hydrocarbon based the energy spectrum towards the more sustainable green energy technologies using hydrogen. So you produce hydrogen from renewables, solar and wind, or nuclear energy. Again, nuclear waste is a problem. The fossil energy sources with carbon capture. There, while producing hydrogen, you are taking water from the environment, releasing oxygen while you separate hydrogen from water. So oxygen going back to the environment. Then you are using hydrogen for application. So whether you are using IC engine or a fuel cell, we are releasing water back. So water you are taking and releasing back. Here you are rejecting oxygen and taking oxygen during the so it kind of looks like a circular, sustainable way of producing or harnessing the energy. Okay. So otherwise, the other model is you can use either hydrogen or electricity in combination, which is produced from renewable energy like solar and wind. You can use the solar energy, or you can use the wind energy, which are cleaner, to produce electricity as well as hydrogen. You can use a combination of these two. When you have excess electricity, produce hydrogen, or when you have more electricity required, then you produce electricity from hydrogen. So in a combinational way, we can use this electricity and hydrogen for different end usage applications in a more sustainable way. Okay. So on a lighter note, I would like to show a smaller video, especially with respect to hydrogen vehicles. I'll rest my today's talk here. I'll be talking about more about hydrogen storage for stationary applications on Friday's class.
Thank you, sir. Dear participants, any queries? If you have any queries, please raise by unmuting your audio.
Yeah.
Hello, sir. Chintan Pandya from Pacific School of Engineering, Gujarat.
Yes.
Sir, actually, I have a question about uh, hydrogen storage. Is it in the liquid phase to the in the high pressure? Like you said, the Babel heat exchanger.
Pardon
Yes,
me?
sir.
Can you come again?
Hydrogen store as in liquid phase with the using a high pressure.
No. To liquefy hydrogen, again, you have to compress it to high pressure. That's what I told.
So okay, sir. The liquefied hydrogen. So
Any gas liquefaction requires isothermal compression to very high pressures.
So, sir, my question is, like, what will be the effect for the using the hydrogen storage in the tube? Well, means the in the like I think that's a 15 bar pressure. So, what will be the effect in the tube?
Which tube?
Tube in the hydrogen heat exchanger.
No. See, your question is not clear to me. Whether you want to store hydrogen in compressed form or liquid form or solid form, while you are putting in the tube, whether it is in compressed form or liquid form or in solid form.
Okay. But actually, what will the effect of the pressure in the tube level into the
We
during
have
the
different cylinders with different storage capability. If you take a metallic cylinder, usual normal metallic cylinder, it can store only up to 150 bar. The conventional commercially available metallic cylinders.
Okay.
If you go to
Commercial
composite cylinder, they can go up to even 800 bar.
Okay. Thank you, sir.
Okay. Right now, we have fuel cell cars available in the market which are using Type 4 cylinders.
Yes,
For buses,
fuel
even trains which are running in different countries, they are taking the hydrogen in compressed gas form at
Yeah.
800 bar.
Yes, sir. Thank you, sir.
Yeah.
Sir, good evening, sir. I am Dr. Ali Rani. Am I audible, sir?
Yes, madam.
Sir, what about the production cost in comparison with our conventional electrical energy? Like we are getting electrical energy from solar or hydro power generation. So what about this production cost?
Production cost of hydrogen you are talking?
Yes, sir.
We should not compare the cost of hydrogen with the cost of electricity, madam, because hydrogen can be used for different applications, not only for power generation. It can be used for different applications, and it is especially if you compare the production methods, it is much cheaper using the reforming methods now. Of course, electrolysis is costlier, but people are promising that they will bring down the cost per dollar, 1 kg per dollar by 2030, which is very compatible with any of the other fuels. We have to compare the cost of the fuels. So electricity is a kind of energy which can be used directly for many applications. We can't compare the fuel with the energy, form of the energy.
Yes, sir. Sorry, my question is strong. In comparison with lithium, like battery.
See, the battery Battery pack you are telling, you know.
Yes, sir. Yes, sir.
So battery pack, see again, you can't compare battery pack with the hydrogen. You know, you compare with the total overall the vehicle with the battery as an electrical vehicle, and the other vehicle with the hydrogen storage device as well as the fuel cell. So right
Yes,
now the fuel cell vehicles are much costlier compared to the battery vehicles. So that's why the market is now being occupied by the batteries. So it is more
So in future,
commercialized.
sir,
In future,
Yes,
yes, because the problem is again batteries, people will realize after 20, 30 years what to do with the batteries whose life is over, and the range you can obtain, right? But whereas the fuel cells are having a longer life compared to the batteries, okay, like any other normal engine, and the range also can be higher once you can store hydrogen at a larger capacity. And moreover, the filling of hydrogen becomes easier when compared to the charging of batteries. So it is not there is a competition between these two always.
Yes, sir. Thank you, sir. Thank you.
Thank you. Sorry, sir, it's already 7:42. I need to catch up with other things. If any doubts are there, we can address it in the next lecture. You know.
Anil Kumar sir,
Yeah.
on behalf of Department of Mechanical Engineering, Lecturer College of Engineering, thank you so much, sir, for his insightful and thought-provoking presentation on hydrogen storage, hydrogen generation. Sir, your expertise and in-depth knowledge on this cutting-edge topic have truly enlightened us. Your discussion on the advancement in hydrogen storage technologies, practical challenges, and the possible solutions was both inspiring and informative. We are deeply thankful for the time and effort you invested to make this session both engaging and enriching, sir. Thank you so much, sir.
Anil sir.
Anil sir.
Vijay Kumar, sir.
All the participants, please switch on your videos. Videos. Anil sir just left, I think.
Anil sir.
Yes, sir.
Sir, we have a question from question answer session, sir.
Sir already left the team.
Sir.
Left, huh?
Yes,
Anil
yes.
sir has left, sir.
Okay. Okay, sir.
Kamalapriya madam.
Sir, shall we have the,
You can start the second session.
Yes, sir. Hello.
shall we have the photo session, sir?
Hello. Ask the participant to switch on their videos.
Yes, sir. Yes.
All the participants requested to switch on video for 30 seconds.